building level information, and it has a global applicability. Okay. So first of all, we ask the question, why, why do we need detailed urban morphology, or rather, how do models see a detailed urban morphology? So this graph here shows example of Budak LCZ-based building heights, and what is a realistic representation of Chicago buildings. As you can see, the Budak LCZ-based, it has very different distribution of buildings compared to how the realistic picture is in Chicago. This is for LCZ1, which is the high-rise buildings, but this is consistent across all the local climate zones. So another reason why we need building level information is to study the heat vulnerability studies. So as you know, if you have a place where you have a sky factor of say 0.5, and if you have a place where you have a sky factor of 1 or an open sky, the temperature is not going to change much. But if you want to put heat mitigation strategies, you need to have information about the mean radiant temperature. And to calculate the mean radiant temperature, the shadows due to buildings also play a role in combination with the trees. This map here actually shows how different parts of the time, different points are shaded because of the trees and the buildings. So initially we started off GLOBUS about a year back as a predictive model. So we initially used the Microsoft building footprints and the OpenStreetMap building footprints. But as it turns out, there is some issues with the coverage. We do not have near global coverage, and also some footprints are missing. So we developed our own segmentation algorithm where we feed in a 3 meter, rather coarse resolution satellite image, which we can use and publish. Don't go on this. This is actually a Google Earth image, which is a much higher resolution. But then we use a segmentation algorithm to calculate the building footprints. So the one in the middle is actually the ground truth in Vienna, Austria, and then we have our model, and this is how our model predicts the building footprints. The next step is to assign heights. To do that, we use a lot of spaceborne products. One is the Advanced Land Observation Satellite, or the ALOS, and then we used a couple of spaceborne altimeters. One is JEDI, which was previously talked about, and the other one is ISAT-2. We also use the population density, because if you see a higher population density concentrated in a smaller building footprint would correspond to taller buildings, as you imagine. Next, we validate. So we used a random forest model, by the way, to assign the heights. So we had two data sets. One was the validation data set, which is just the 20% of the data which was left over after training. And here we have the validation. So overall, we see that it performs well. And we also see that the model has a tendency to underestimate the heights of the taller buildings, while there is a slight tendency of the model to overestimate the heights of the low and mid-rise buildings. And this is for both the training and the testing, the validation and the testing data sets. An important thing to remember here is that we retain the heights that are originally available in the OpenStreetMaps in the past. Here's another validation of one of the urban canopy parameter, or the UCP, called as the building surface to plan area ratio, which is the ratio of the total urban surface to the grid size. And we're showing result for Austin, Texas in the US. The model was trained over the US, so it performs very well. We also validated it over Madrid in Spain. We get reasonable agreement, and the graph here shows how the building histograms are. So this shows the building heights, which are less than 15% in Houston, Texas. We see that we capture the heterogeneity quite well. But this segmentation and assigning the heights is a very expensive process, as you would imagine. The data processing that is required to do this is quite large, although the model runs very quickly because it's a machine learning model. But at that time, our collaborators at Purdue University were working on this graph neural network, where we just give the road networks plus some prior building footprints, and then it could generate the entire city. The idea here was not to generate one-to-one match with the reality, but to give people the data so that they can calculate the urban canopy parameters. And then we thought, why not we use the heights that we produced using GLOBUS into this model and generate the entire city just by giving a fraction of city. That's exactly what we did. We modified the model a bit, and then here are results. So this is Austin, Texas, and Chicago. What we have on left side is the globus, and on the top is the globus, which is representing the truth, and then we have the generative model at the bottom. So with this, we have also calculated the urban canopy parameters, and we find that there is a good match. Right. So I'm going to show you a few applications, one at the city scale and one at the street scale, because oftentimes people ask us, what do we do with this data? So this data, Globus, actually interfaces quite well with the WRF modeling system using the existing NUDACT framework developed by Dr. Ching here. So we start with building polygons, which is a building level data, and then we extract the urban canopy parameters that are required for both the single and multi-layer urban canopy models. So these are the things that we can extract, and we have automated this with this QGIS plugin that we wrote to get this data out of it. And then we still need some more data about the buildings, like for example the roof albedo, emissivity, etc., that we can extract from the local planet zones, and then this goes into the geogrid, and then that is read by the work model that I'm doing. And yeah, this is following the NUDAC framework. Here are some quick results. This is the land surface temperature in Houston during noon. The one at the left is ecostress. Ecostress also has its own problems because it's a satellite and it does not measure the complete urban surface. But what we did in WRF is that we just took the temperature equivalent of roofs and the streets so that we can compare it with the satellites. Here are the results. So the simulation that we have is Globus UCBs and the default LCZ UCBs. We can see that the spatial heterogeneity is better captured when we use Globus compared to the LCZ. Although when we calculated the RMSE, the LCZ was lower. That's because in the southern part of the city, for some reason, as you can see that the model with Globus did not perform well. But overall, the heterogeneity was very well captured. We saw if this could be reproduced using the air temperature. So we had some data set where we used cars to traverse around the city, and then we interpolated it on the WRF grid. Here are the results. So you have the mobile traverse data, simulation with Globus, simulation with LCZ. So as you can see, most of the times the simulations with LCZ are over-predicting intermediate temperature, and this time we get the RMSE to be lower when we use Globus. We can also use this to test out the efficacy of the heat mitigation strategies. We do not have anything to compare it against because we do not have any experiments that have a log scale. So this is the control experiments in which we are not implementing any heat mitigation strategies in Globus and using the LCZs. But when we put the cool roofs, we see that the LCZ has a tendency to unrealistically cool the city. That's because the plan area fraction is not accurate. But when you use Globus, you get better results. Similar results with the green roofs. So we put green roofs at 60% of the urban grids. You have the control cases with the Globus data and the LCZ. And green roofs have a tendency to have a nighttime warming because it is a well-irrigated soil on top, and then it can't radiate the temperature. Here we just see the potential for nighttime warming using both the data sets. We see that the warming is different when you use different data sets. Here is a complete picture where we use the daytime and nighttime using three heat mitigation strategies for the cool roofs, green roofs, and the cool pavements. An interesting thing to know here is that cool pavement has a tendency to increase the temperature. That's because when you make the roofs more reflective, it reflects off the radiation that's captured by the roofs, and then that increases the wall temperature that diffuses and we are using the building energy model with this. So the anthropogenic emission increase because of that, and that's actually captured with Globus in compact regions, but not the local regions. We can also use it to study the urban energy. This is cooling energy demand and PV power generation. You can see when we use the local climate zone approach, the AC energy consumption is quite uniform because the world considers the urban canopy parameters using the near-edge neighbor interpolation. But when we have the Globus data, you have much more heterogeneous. Plus, at the downtown, where you have taller buildings, we see that the energy required for cooling consumption is much higher, which is really stable. Same goes for the PV energy generation. And we also calculate the fraction of PV energy generated that can be used for AC cooling. We see that using Globus at the downtown area, this ratio is very less. That's because the top buildings are taller and the plan area fraction is not enough to meet the heating demand when you put the BD. Some application at the street level using UV Globus. So here we just considered the buildings and we're modeling party board and we're using solvent to do that. So here is the mean radiant temperature using the LiDAR, which is a control case, and you have the Globus readings. This is the daytime data, good agreement, uh, especially in the downtown area where you have taller building that cast shade, and which means that the mean radiant temperature is lesser. Nighttime again, this time the downtown is warmer because the walls are warmer and then they are radiating long wave radiation, and that's also captured. And as you can see with the RMSE, we are going to be good. So how can we use this Globus data set for decision making or even planning heat mitigation strategies? So we came up with this index called as a Human Heat Health Index, or H3I. So what I'm going to focus here is just on the hazard, which we define as the UTCI, which is calculated using the building Globus buildings. And trees, right now we are using the LiDAR trees, but we have a project where we are also calculating the tree heights and difference. Right, so what we do is that we take the UDCI, and 32 is the limit where it becomes dangerous. So we subtract it and we actually calculate the cumulative time of the day when it is hot. Rather than using urban heat island intensity, I think we think that this is better. Here's our data availability. So this is the data sets we have, about 330 cities in the US and 300 cities in Europe. So when we see urban area, it also includes the suburban areas. So the file sizes can vary up to say 100 megabytes to 500 megabytes. These are vector files which can be rasterized and used in Solvay or Swiss model, or we also provide the binary files for work directly ingested into the preprocessing system. So when you see this animation where we have Globus data overlaid on the Google images, Google satellite image, the two main takeaway points that we consider would be that UT Globus data interfaces with the work system, and then we can use the UT Globus data to study heat hazards. Thank you.
Thank you, Harsh. That was really interesting. Do you have any questions for Harsh?
Yeah.
That was marvellous, well done.
Thank you.
So the plan's obviously to make it globe plus, right?
Yes.
So can I ask you, where you did the comparisons with the convention LCZs, the LCZ obviously have ranges rather than specific values. So what you're doing is you're just putting the median value in?
The mean value.
The mean value?
Yes.
Okay. So let me ask you a related question. Does that mean that do your values fall within the ranges of the LCZs? Are in fact are the ranges incorrect? Or is there an error associated with the production of the LCZ map itself?
I think different cities are different, so I think this was for one specific city that the LCC urban canopy parameters were defined. But then, if you look at LCC somewhere in New York City, right, or compare it with LCC one in say Paris, these are totally very different things. Because Europe tends to have a higher plan area fraction, where cities in the US tend to be different, and Asian cities are different. So that's why we started to move away from local planning zone approach, at least to parameterize the model. LCD is still very helpful as a diagnostic tool to understand the neighborhood scale heat, for example. But when you are modeling, I think we need much better data.
Any more questions? Yes.
Hi, thank you for the presentation. I was wondering, since you use running forest as a predictive model, have you tried to look at like other models, and do you think the overestimation of the low building and underestimation of high building is related to the fact that that could be a potential limit of running forest?
Yes, we did look at other models. We actually started off with computer vision algorithms like SRC and GANs, and we found out that the tabular data is better when we assign the heights. In tabular data, we also tried XGBoost and all this, and even all the models were hyperparameterized. The reason why we are getting underestimation of taller buildings is because of are input data sets. Like for example, all of these are static data sets, and when you have urban sprawl, for example, that is not captured. So that is why our mean heights go down, and we cannot sometimes get the heights of the taller buildings. We use Jardine eyesight to kind of address this, but then this only gives us some transect over the city. If the transect doesn't lie over the recent urban sprawl, then we cannot capture that. We have to just rely on the random forest and the population density to prediction. Yeah. Yes.
So I'm trying to catch up. Is GLOBUS global?
It has global potential. So right now we have 330 cities in the US and 300 cities in Europe, but we have the potential to do that.
Are you familiar with the database that Japan has come up with called Plateau 3D?
Yes, but I'm not sure if it is open source.
Oh yes, that's what I found out.
Okay.
So it's a real opportunity.
Okay.
So if you have GLOBUS, then you could almost have a chance to verify what your products from GLOBUS would be against real data, which is, I think, your LiDAR is
Okay.
data.
Okay.
So this is an opportunity.
And what are the plans for expanding Globus outside?
Yes,
North America?
there are. So right now, although we're not sure, we have some Indian cities. So when people come to us asking for some data, we just process them and give it to them. So
And you can process across a large area in a how much processing will you require to process, say, India?
so the predictive model, it takes a lot of time. That's why we are moving towards this generative algorithms, which are really quick. So we can just do that within minutes for like an entire city.
Wow.
Well,
All right.
So, just to add, I was hoping Harsh should show the Sydney one. So when we started the Sydney and Australian cities, they asked, that time it took us about a week, I think, to get that thing going. Now when we are doing it for India, it's sort of like, distributed cottage industry. You can create it as you want it. But the difference here, that when we say there are building height data available and there's the UV globus available, is not so much that it is the building height data. It is really the building height data that interfaces for creating the parameters that are read by the model. Because it's not really that the model reads the building height per se, but it is what happens after that. And that interface with, say, Word or any other model, where we are actually going with the parameters that are required, that I think is the real strength in terms of what is being done here. And that's quite independent, and it doesn't, like, I think Nitin made a good point. You often create multi-errors. First error in mapping, second error in characterization, third error in maybe initialization and so forth. So we are trying to cut down on that.
I actually think you're selling yourself short there.
Thank you, Gerald. Please do
I don't think it's just WARF.
Yeah, totally, yes, Solvage and whatever we have.
But also all the social economic models of cities.
Right, so the building height and the energy use that is
And once you get trees in there, you'll be able to look at equity issues, all sorts of stuff.
It's certainly one of the parameters that's constraining our large scale modeling. So it's really interesting to see. So thank you very much.
Thank you, Matt.
So I think that wraps it up for the session. Thank you to all our speakers and thank you to the questions.